Welcome to all. This is also a requested video. I thought of that I will simulate it, live simulate it. Today we are going to discuss about a special criteria of fracture mechanics. That is whether if there is a crack, and after applying the external stress, whether it will propagate or it will not propagate, or this will if it is propagate, then whether it will be going towards a brittle fracture or not. All these things we are going to discuss. Anyway, I am not expert on that, but I did one finite element modeling of that. I thought I'll do the same. I started to model that, but because it's a transient analysis, so my laptop is memory is very less, and there is no graphics card, so it's not the solver is not getting converged. I tried for 2-3 days, but it's not getting converged, so that I will share. So I thought that I will share the things what I learned from my guru, because basically I am electronics engineer, but this it was taught to me by Dr. Chelapandi, and definitely I should mention one name, Amitabh Bishwas, who is also was an expert in fracture mechanics. So anyway, I am going to just analytically, and I'll try to show the simulation. Then it will be graphically. It will be, once it is seen, then the concept will be very much clear. So today I am just going to share you what I did long years ago. So to understand the crack, the first thing which is to be understand, that is the stress concentration, how the stress concentration will change if there is a crack and we are applying some external stress. There are various modes of crack. So today we will be talking about mode 1. So that is opening, crack when it is getting opened. So let us take this is a say this is a plate, and there is a crack here. Okay, so the crack length, so this is, let's take this crack length is 2a. Okay, and as it is opening, I told this is the mode 1, so crack is getting opened. So here my applied stress, and this side also. So what will happen, this crack will get opened, means it will become like this. It has become like this. Okay, and one more thing we will here consider, the tip, the crack tip radius, this tip radius, this tip, say this radius is, crack tip radius is rho. Now we will plot, we will try to plot the stress concentration distribution from the tip to the the x-axis is the distance from the tip of the crack, and y-axis is the stress concentration and or the distribution. So these things, the instantaneous the or the maximum stress, the maximum, we know the maximum stress will occur at the tip only. So this maximum stress sigma max, which is given by, it's very basic things I am telling, because I studied these things. I can remember during my third semester I studied the strength of material by Timoshenko. So that from that book only I am writing all the expression from that book only. I think this is the basic book, all you have studied that. So this is the sigma max is equal to the applied stress into 1 plus 2 times of crack half length by the tip radius. So here it is very clear, if the tip radius is less, then the stress is maximum. That area stress is maximum, means it is higher than the applied stress. And if the crack length is more, then also the maximum stress will be more. Okay, from this equation it is very clear. Here we give name, say sigma A, means sigma applied and sigma maximum. Now if we plot it x-axis, so here means this origin is at the tip, the origin is at the tip of the crack, and we are going away. The applied stress, it will be constant, but say this is the stress applied on the plate. So this is a constant stress we are applying on the material. But if we see at the tip, so at the tip this rho tends to 0. So this is very high, and once you are going away, then this stress will less and it will be like this. Okay, so this concept is very important to understand the crack propagation. That means if there is a notch, in the crack, if there is a notch like this area, the stress concentration is very high. That's why if you see in the locomotives or in the aircraft, the openings, the windows, if you keep like rectangle, so what will happen? So this area, this corner, the stress is very high. The stress is very high. It's because the radius is nearly to 0. So it is infinite stress will develop there, and the crack will propagate. If that if due to this sharp notch, if the maximum stress cross the critical stress, then it will fracture. The fracture will take place. Okay. Anyway, today we are going to. That's why in the locomotives, bus, which is the moving means the vehicle, we will not, in the window, in the opening of the body of the in the body of these locomotives, aircrafts, or this kind of things, the openings will be don't have this sharp edge. It will be either this kind of things. it will be slightly like this. There will be a corner. So the maximum stress, even though there is some external force applied due to the vibration or something in aircraft due to the gyroscopic couple and all these things, then this stress will not cross the critical stress. Okay. Anyway, today we are going to talk about the ductile fracture. Brittle fracture. So you know this in the ductile fracture, it is all we know. It is like this. So if there is a crack and we are stress applied, so this is a purely ductile fracture. Here we are applying the stress. Okay, this side. And moderately ductile means we can see it. So it will be like this. If you do the tensile stress, the tensile test of any bar or these things like this, so it is just most of the cases we will find these things. It is a moderately ductile. In brittle, there will be no deformation. It is break. These are the something case of it is a tiered, but here it is break. Two parts are separated like this. So this is called the brittle fracture. So we are, if these two cases, there is a possibility of these two case, first two case, this is say case 1 and case 2. If this kind of things happen, there will be the possibility of leak. But if the case 3 happen, it will fracture. The catastrophic failure of the structure will take place. So we are going to talk today, if there is a structure or pressure vessel or pipe, then what should be the design criteria, or what should we consider that this kind of brittle fracture will not take place. It will just leak. In case we are some crude, it's a kind of inflammable liquid, explosive or something, or like our nuclear reactor, fast reactor coolant like sodium. If it is like that, a brittle fracture will take place, then suddenly huge quantity of coolant will come out, and this will cause the exothermic reaction and explosion will take place. So better we will always think if there is a leak also, so this can be controlled, the hazard can be controlled in some extent. Okay, so this brittle fracture criteria first was analyzed by Griffiths. So we will see how it was analyzed by Griffith. So when there is when the crack will propagate, if we apply some energy, if we apply some external energy, and if it is not getting decreased, that means my crack is not getting propagated. If it is my external energy, the mechanical energy which I am applying, if it is getting decreased, that means that is spent in strain energy, because there is some elongation, okay, and some work done is taking place. Okay, so if the applied energy is not getting decreased, that means the crack is not propagating. If it is increasing, that means it is absorbing, like a it's a spring action, like pre-stress. It is the things is getting absorbed. So let us consider the energy in take a plate if it is not cracked. Okay, so this is the energy of uncracked structure. Okay, and say this is the energy, mechanical energy of this is uncracked, and this is the mechanical energy of the cracked plate. Okay, so here it is very much clear that this energy, if I subtract from EA by E0, so this will be higher and this will be lower. So the change of total mechanical energy due to this crack propagation or something, whatever you tell, if that is delta EM, and that is the final energy minus the initial energy E0. Okay, as I told, so definitely this quantity is lesser than the initial energy applied, because some work done and some the energy spent in the elongation or due to the strain. Okay, and this value is empirically can be written. It is the standard formula, pi sigma applied square into A square, that is the A is the half length of the crack, and say the B is the width. That means if you see the previous picture, so this length is 2A, this is 2A, and this is the stress sigma, this is the sigma, and if there is a width of B, I am considering that width is B, so that is minus pi sigma square A square B divided by the Young modulus of the material. It's a standard formula. Now the another energy component is also responsible for the propagation of the crack, which is called the change in surface energy. Because if there is a propagation, and as the first we have seen that there is a stress distribution, so there will be also a significant change of surface energy. Okay, so that we are defining as delta ES, which is given by, so there are two surfaces, one is top in the crack, one is top surface, another is the bottom surface. So I am assuming the surface area at the top of the crack and the bottom of the crack are same, so it's 2 times, and the length of the crack is A and the width is B, so this is the total surface area, into, I am defining one variable here, gamma, which is surface energy per unit area of the fracture surface. Okay, so now this is the total change of energy. This is the total change of energy taking place. One is the change of mechanical energy, which is delta EM, and the change of surface energy. Okay, so this is the total energy change. This is the total energy change, delta ET. I am telling E total, which is delta EM plus delta ES. Okay, delta ES. Okay, so now let us try to plot the thing. I am deleting this page. We will plot this the total energy change total energy, this all the component we will plot as a function of the crack length. This is the crack length A. Okay, so the delta ES is the surface energy change, which is equal to, we have seen it is a 4AB gamma. So this 4AB is the crack length and breadth of the plate. So that is constant. So basically this ES, delta ES is proportional to, the formula is 4AB and gamma. So these quantities are constant, then this ES is proportional to A. So it is a positive slope, so you will get like this one curve, so which is delta ES. Okay, now the delta EM, what was the delta EM? So if you remember, it was minus pi sigma square A square B by Young modulus of the material. So we can tell it is proportional to minus of A square. So you will get a curve. It's a, you see, y square is equal to 4ax, that is a parabolic equation. So you will get things like this. It's a parabolic equation. So this is your delta EM. Now if you sum this, the total energy change, these two, if you get the summation, you will get a curve like this. Am I right? So this is the delta ET. Now if you see the red color curve, this having a maxima. Here it is maximum. Here it is maximum. Okay. Now we can draw one important inference from here. Say I am giving that point value, the critical crack length AC. So if the crack length is below AC, then what will happen? The total energy is getting increased. Correct? So the total energy is getting increased. That means it is stored in the structure, like it is getting pre-stressed. So like the spring action. So the crack will not propagate. But if the crack length is higher than the critical this AC, then what will happen? The energy is getting decreased. The total energy is getting decreased. You see, it is getting decreased. When this decrease, how this energy will decrease? If the energy is lost due to strain and the work done is taking place. So that means the crack is getting propagated. Okay. So now, if the crack length is less than the critical crack length, then that crack will not grow. It will not grow. And if the crack length is higher than the critical crack length, then it will grow and the fracture will take place. That means, here one important thing, if there is a crack in the structure, in the pipe or in the vessel, which is lesser than the critical crack size, then what will happen? It will not propagate. Finally, it will create some leak. The fracture will not take place. But if the crack size is greater than the critical crack size, then that catastrophic failure will happen, and it will cause the brittle fracture. Okay, so this condition is called leak before break. Breaking will not take place. It will leak. At most, it will leak. We can take some preventive action to do that. But if the crack length is greater than the critical size, then it will break, and entire inside whatever the liquid or the hazardous fluid, it will come out. Okay, so during the design you should consider this criteria, these two things. So definitely, if there is a crack, that always should be lesser than the critical crack length of the material based on the material property, which is given in the ASTM standard. We followed ASTM. I think in our large diameter sodium piping, it is P91. It's around 1 meter, 2 meter die. I have seen how brittle nature it is. It is very hard. I have seen how it is pressed and it is made that pipe. So many times that die broken. I have seen. It's very hard material. So now we'll try to quantify this a critical crack length. So from the curve, it is very clear that at the maxima, when the value of ET is maximum, the value of crack length is called the critical crack length. So the expression is given by del ET. So we can tell what we can tell. The del, if we differentiate any function at its maxima or minima or extrema, so that should be 0. So del ET by del A with respect to the crack length, this is at A is equal to AC. I am defining that particular crack length is a critical crack length. That should be 0 because it's a extrema or maxima. Okay, so now if you see the total expression of del ET, so that is the change of mechanical energy, which is minus pi sigma square, that is the applied stress, into half crack length square into the width divided by the Young modulus of the material, plus the change in surface energy, which is 4 times into crack half length into width into the surface energy per unit area of the crack. So now if you differentiate this ET with respect to A, so here it will come, this other things are constant, so it will come minus pi sigma square 2A B by Young modulus plus 4 beta gamma, 4 B gamma, that is equal to 0. Then this B will be cancelled out, and here this A means AC. So your AC is the critical length, is critical crack length is given by 2 gamma times the Young modulus divided by pi sigma square. Okay, so this is the, from the Griffith's criteria we can derive the size of the critical crack length, which is AC, that is 2 times of gamma into Young modulus divided by pi into sigma square, which is the applied stress. So now for the safe design, means it is, if there is a crack also, let it leak before crack, it should not propagate. So I will plot another curve here. So this side, that the x-axis is my applied stress and my y-axis is the critical crack size. Again, this, if you see, this 2 gamma, Young modulus, pi, all are constant. So this is a, things are coming, it's a like a it will come like a parabolic function. Okay, so this will be, these things, it will be like this. So now for a certain particular point here, you take a point here. Okay, so say this is sigma A1. So for that, this is your critical crack length. Now say there is some crack whose length is this much. Okay, so if you here that criteria, so this is my crack length. So what is there, if there is a applied stress also there, but my crack length is lesser than the critical crack size, so this will not propagate. At most it will leak. So what I mean to say, the region below this, curve, this green line, is always safe region. So this is safe region. So if you select your design so that the parameters are falling beyond this green curve, then there will be no brittle fracture. At most it will leak, it will not propagate. So this region is safe, and that region is called leak. This criteria is called leak before break. But if somewhere this point is, your crack length is something here, okay, so you see, that is, if you select this region above the green curve, say this is A dot, which is greater than my AC1. Okay, so this means, as per the Griffith's criteria, the brittle fracture will take place. So this region, the region above the green curve, it is called unsafe region. So during your design, this should be taken care. And whatever I discussed, these all are these are the mode 1 fracture. So your mode 1 fracture, so I'll try to draw the mode 1 fracture will be, as I told, it is opening. So mode 1 fracture, if there is a fracture, it will try to open. Mode 2, means sharing. It will go like it will go like this, okay? And tearing, it is like this. So we are talking about whatever we discussed, that is mode 1. It is a opening type of fracture, opening, not sharing, not tearing. So here I want to introduce one more thing, one more variable or one more constant. Let us name it as G1. This is the, as I told, all we discussed about the mode 1 fracture. So this is the G1, which is strain energy release rate. Strain energy release rate. So definitely strain energy release rate will be dependent on the surface energy, which is nothing but I am defining one more constant, K1 square by Young modulus. Okay. Now, as this things is quantified as the strain energy release rate, so that is nothing but the decrease of surface energy per unit area. So there are two surface, and we define that is as the surface energy per unit area is gamma. Now my new variable Ki square, it is defined as 2 gamma in gamma times the Young modulus. Okay, so this is termed as stress intensity factor. Okay, and when this value, this constant, is related to critical crack size, that at critical crack size the stress intensity factor, so that means the K1 at crack length is equal to critical crack length, that I am defining another constant which is KIC, that we are named, that is called the critical fracture toughness. Now if we, so this value only given in the, this value will be given in the ASTM standard. I can't remember the ASTM for P91, but I forget that it is given. The K1C is given. The critical fracture toughness will be given in the ASTM. Okay. So now we will write down the critical crack length formula in terms of this critical factor toughness. So this K1C is basically 2 gamma times Young modulus. So this term can be replaced by a KIC square. So this is nothing but the critical crack length is equal to 1 by pi K1C is a Roman 1 mode 1 fracture, opening type of fracture, by sigma whole square. This is the standard formula. So now we will go for a particular example. whether this leak before break criteria is satisfied or not. Take an example. This is the pipe, the large diameter sodium piping of P91, 9 chrome 1 molybdenum, and this is the thickness. Okay, take the thickness, because the thickness was around 20 mm exactly. I can't remember, but it will be around 20 mm. So this is my thickness T of the pipe. Say the inner coolant pressure. The coolant pressure is it is more, but you take, it is say 10 megapascal. Okay, and the diameter of the pipe, say it is 1 meter. Huge. In our case, there is most of the pipes are 800 NB. We will take typical example of 1 meter. And for this material, say from the ASTM standard, I got the critical factor of the critical fracture toughness is given by say it is 200 megapascal square root meter. This is the unit. Because if you see here, if you see this equation, this your K1C is equal to this K1C is equal to let us write it. So this K1C is equal to sigma into root over pi AC. So pi is unitless, sigma is in megapascal here, and this will be in meter. So that's why the unit is megapascal square root meter. So this is the value given. From this data, we have to calculate, we have to predict, or we have to decide whether this leak before break is satisfied or not. Okay, whether this, if any crack is there, whether it will propagate and cause the brittle fracture, or just it will leak out. Just the liquid will leak out, and so that we can, it is manageable, and we can control the hazard. Okay, so that from this data we know it's a kind of, like, we can consider a spherical system, or here we can find out the like for one spherical vessel or something, the stress, the applied stress is given by P times of the radius divided by the thickness, 2T, double of the thickness. So from there we can find out, we can find out the, we can find out the applied stress. So we know the applied stress, and we know the critical fracture toughness. So my critical crack size, it can be calculated using this formula. Sorry. So your sigma is this, and your K1C is this. So you will get some value. numerical value. Now here we can, if there is a crack also propagated or something like that, if a full crack is there, so the maximum thickness is 20 mm. So if this value, if this 20 mm is lesser than the value which we will be obtaining from here, that means it will cause leak. The brittle fracture will not take place. Okay? And what is the safety factor we have considered here? So the safety factor is my K1C divided by K. So definitely this should be greater than 1 in case of leak before break. Okay, so that means that value is K1C we will be getting from the ASTM standard based on the material property, and the K is sigma from this equation. It is sigma pi A. Okay, so again the sigma is, so here the sigma is this sigma, and A is the thickness of the vessel. So basically this is the but I will definitely I will try to show the simulation. I have seen that I got the problem statement. I tried here to last 2 days, my PC was running to converge the solution. I did it in console, but this is not getting converged because my graphics card and the memory is very low. 2 times it is the solution has been halted and I again given, but it is not getting converged. But I am surely I will show these things with 2 different example by simulation, that one case it is fracture will take place and another it will propagate and stop, and leak happened and it stopped. This I will show you. Even though I tried whatever I understood, that I am trying to share. I don't know whether it will be useful to you or not, but I tried my level best to explain it. Thank you so much. Thanks for watching.